when a client is initiating a connection, it sends a TCP packet with the appropriate port numbers with to the server, which is handled by the IP layer, with a SYN field set to 1 and some initial sequence number. Let us assume that it is 0. If the server is willing to accept the connection, it responds to the SYN with another TCP packet which carries the ACK bit equal to 1 and a sequence number value based on 0, which we'll see in detail when we study reliability. Essentially, I would like to say that or a TCP packet with SYN bit set to 1, the server sends an ACK packet or a TCP packet with the TCP with the ACK bit set to 1. TCP does full duplex communication, so it sets up connection on both the sides. So in the same packet, the server initiates another connection in the reverse direction. So it sets the SYN bit to 1 in the same packet, essentially piggybacking, and sends it to the client. The client applies the ACK for its connection. It responds with an ACK for the request from the server as well, essentially leading to another TCP packet with the ACK bit set to 1 and the SYN bit set to 0, as there is no need to set up the connection again. So in conclusion, we have a SYN from the client to the server, a SYN-ACK or ACK-SYN from the server to the client, and finally an ACK from the client to the server. This is essentially the three-way handshake between the client and the server, ensuring the client and server are in the same state or in agreement to the requirements of the connection. A similar three-way handshake happens when the connection is turned down. There is a FIN packet where the TCP packet header FIN is set to 1, and in response to that there is a FIN-ACK, and finally there is an ACK. Now we will see that in a simulation where these are some basic parameters. Simple, the link speeds are 10 Mbps. The link propagation delay is 25 milliseconds with the overall propagation delay of 100 milliseconds. And with 10 Mbps and 100 milliseconds, the overall BDP is roughly 100 packets for packet size of 1460 bytes. We are considering an FTP application with a file size of 14600 bytes. That's roughly 10 packets that we are seeking to transfer. And we will use a simple TCP version of New Reno for the simulation. The objective of this exercise is to file for using TCP and observe connection establishment and connection teardown before and after the simulation. I'll now leave the discussion to Krishna Bharadwaj, who will conduct the simulation and show us the results through the simulator. Thank you.
Good afternoon, everyone. Thank you, Professor. So this is the NetSim standard here. So in the open simulation, we can click on the internetworks. Now here we will have the nodes, wide nodes. So we will drop 2 wide nodes. Then we will connect these 2 nodes with a router. So when we use the wide links to connect the wide node 1 and this router, and the router and wide node 2. Now we need to have an application file transfer between wide node 1 to wide node 2. So we'll drop an application. We need an FTP application. So select the FTP. And we need the FTP application from wide node 1 to wide node 2. So the destination ID, change it to 2. I need a very small file transfer just to know how the TCP three-way handshake does. So just 10 packets. Then we select the properties of this application by clicking OK. Then we see the basic parameters of this wide node 1. At the transport layer, we have the TCP enabled. Control algorithm is Neurino by default. So we accept these properties. And at the link side, in the link 1, we change these properties as shown before in the slides to 10 Mbps and with 0 BER. And the delay we consider here is 25 milliseconds. And we accept these properties for link 1. We configure the same properties for link 2, 10 Mbps with 0 BER and then with 25 millisecond delay. Now we enable Wireshark on wide node 1. We enable Wireshark capture and then we run this network. Just and we also record the animation to show how the three-way handshake does. So once the simulation is done, in the Wireshark we can see, as explained before, the first packet in the pcap file. We can see the first packet, TCP packet, SYN. To visualize more, so in the TCP header, in the flags, we can see the SYN bit set to 1. So this is from the client to the server, and the server is responding with a SYN ACK, and finally the client is responding with an ACK, and we can see the file transfer, and finally the file transfer is closed with fin and finac. The same thing we can visualize using the packet animation in NetSim. We can see a SYN ACK, and then a TCP ACK, and then the application file transfer is being happened. So this is how the TCP three-way handshake happens. Now I'll give it over to Mr. Prasad.
Thank you, Krishna. As we saw in the packet capture, You see that there is a SYN, there is a SYNAC and an ACK, and there is an entire file transfer followed by a FIN and FINAC and an ACK. Thus, we see that TCP establishes a connection using a three-way handshake before file transfer, and the connection is terminated with three-way handshake as well. And the TCP header essentially carries the information. I would like to point here that the PCAP file permits you to review the TCP header in great detail, and you would appreciate by reviewing the packets, including the data packets in Wireshark. With respect to the simulator, you can appreciate the three-way handshake using an animator, or a PCAP file, or in a more rigorous sense using the packet trace. Let's go to the second experiment where the focus is on reliable communication. To appreciate how TCP enables reliable communication, we study data communication over a lossy link, and we focus on how TCP fragments the data, the sequence numbers, and the acknowledgement packets, and finally the concept of retransmission. We consider the same setup as before, except that the links are now lossy, so they lose packets once in a while. We again use an FTP application for file transfer. In the previous discussion, when I focused on connection establishment and teardown, I focused only on the SYN bit, the ACK bit, and the FIN bit. Numbers that are part of the header, sequence numbers and the acknowledgement number. Let's assume that the connection has been established and the client sends a packet of length 1460 bytes. The first packet will carry a sequence number 1 if the SYN packet began with the sequence number 0. The sequence number 1 essentially indicates that this is a packet corresponding to position 1 of a large data file. The packet will carry a sequence number 1 and a length 1460 bytes in the TCP header, and the data will be communicated to the TCP at the server side. In response, the server will respond with an acknowledgement packet with the acknowledgement number equal to 1460 plus 1. That is, the acknowledgement says, I have received 1460 bytes. Now I'm expecting 1461 byte. If the acknowledgement is correctly received, then the client will respond with another packet. Suppose it has more packets to send, and this packet will be starting with sequence number 1461, and it will be of length 1460 bytes. Let's assume that the TCP client will send one more packet. This packet will carry a sequence number 1460 plus 1460 plus 1. 1460 plus 1460, and that will be 2921. Let's assume that these packets are also correctly received at the server side. So upon receiving the packet 1461 identified with 1461, the server will send an acknowledgement with acknowledgement number 2921. Upon receiving the packet with sequence number 2921, the server will send an acknowledgement with sequence number 4381. Let's assume that the fourth packet transmitted by the client, the packet which starts with sequence number 4381. If there is no other packet, then the server has no way to know or acknowledge the loss of a packet, so it does not respond. In this case, the client learns about the loss of a packet through timeout. It has not received any acknowledgement. So after a certain timeout, it retransmits the packet, and upon receiving the packet with sequence number 4381, which is in order, the server will respond with a packet with ACK number 4380 plus 1460 plus 1. And the connection continues, and once the file is completely transferred, the connection is closed. As you can see, the server seeks to receive the packets in order, or seeks to receive the bytes in order, and if some bytes are not received, it continuously seeks the packet starting with that byte position through the acknowledgement. Thus, the sequence number allows the client to identify the data positions using the number, and the acknowledgement numbers allows the server to identify the data which has been correctly received and which is not correctly received. This is how TCP ensures there is reliable communication or transfer of data between the client and server. We will repeat the same experiment, but with a small modification that the link BER is no longer 0, but now it will be 10 power minus 5. I'll leave the floor again to Krishna to show an experiment of reliable communication using NetSim.
Thank you, sir. Again, we will consider the same network setup. So in the previous network setup, we didn't have the link BER. So now we consider the link BER as shown in the previous slide. As we have enabled Wireshark, we can see the traces in Wireshark, and we run the same in network setup. So in the previous case, we haven't seen any packet drops. Now, since we have enabled the BER in the one, now we can see a packet being dropped, and then there is a retransmission of that packet, and finally there is an ACK for the packet. So once the packet is successfully received, it will be ACKed, and then the TCP ensures that the connection is completely reliable. And finally, the TCP session is being closed with the fin and finac. I hand it over to Professor.
Thank you, Krishna. Thank you, Krishna. So here I'm repeating the PCAP, but from the server side. If you look at the PCAP, you can realize that the first 4 packets are correctly received. However, at this time, a packet is received not in order. So the message already says that the previous segment of the TCP was not received. And so the same acknowledgement number 4381 is sent again. That's why we call it as a duplicate ACK for the byte position 4381. And for every packet correctly received, it sends the same acknowledgement number. So we have multiple duplicate ACKs. And upon receiving 3 duplicate ACKs, the client would respond with this packet 4381, which is identified here in line 21. The out of order packet is received with sequence number 4381, and upon receiving it, the server responds with an ACK 13141. It has stored all the other packets which were received out of order in the receive buffer, and the ACK sent in line 22 is a cumulative ACK acknowledging the correct reception of all the bytes till the position 13141. The last packet of the 14600 bytes is sent, and finally the connection is closed down. As suggested earlier, the sequence numbers and the acknowledgement allows the TCP to identify the amount of data correctly transferred and the data that is not correctly transferred, and thereby ensuring a reliable, orderly delivery to the destination. Conclusion on this part is a file is typically transferred as multiple segments, with each segment carrying its own header or identification. The sequence numbers associated with the files help track bytes received and transmitted. In general, in any network, packet losses can occur due to channel errors, buffer overflow, congestion. And the sender side, which is in this case the client, learns about the packet loss either due to timeout or due to multiple duplicate acknowledgements. At the end, once the file is completely transferred, TCP terminates the connection. Once again, we can view this in great detail using the PCAP file, and many of these details about the sequence number and acknowledgement can be reviewed better by reviewing the TCP header.